to talk about is VRF, right? VRF is a variable refrigerant flow system. And I'm going to be showing some slides from Daikin's training class on VRF. And they call theirs VRV. So VRF stands for Variable Refrigerant Flow. VRV stands for Variable Refrigerant Volume. In the grand scheme of things, even though Daikin will tell you, VRV is special because XYZ, in the grand scheme of things, they're all really similar. So when it comes to mini splits in VRF systems, the heat pump systems are not super special, other than you can have multiple indoor units connected to a single outdoor unit. And the capability to do that has been around for a while. It doesn't take much to just throw a T in a refrigerant line and connect multiple indoor units, actually. Your metering device needs to be at the indoor unit if you're going to do that. But it's actually not as complicated as it would seem, although to get it to work well, it does start to get complicated, right? Because you need to control the flow of refrigerant and you need a variable capacity compressor or a lot of staging between a lot of compressors to do so. The fact that we have a lot of variable speed compressors now makes it a lot more viable to do multiple indoor units connected to single outdoor units. So with mini splits, we kind of started off there with just having like a single header on the outdoor unit and then running line sets to the individual indoor units. In a VRF system, it's always been run a set of line set and then Y off the refrigerant lines to other units. And I say Y specifically because you don't use straight copper tees, right? They have special fittings that are made to kind of help the refrigerant flow in different directions, similar to a Y in a plumbing system. Daikin's really looks like a Y. Carrier's system, it looks more kind of like a horseshoe. So they all have kind of different designs on where that split is made and what those splits look like, but they're not just like a T going off one way and a T going off the other. You can't really do that because you want to try and give on full load applications, you want to give that refrigerant a chance to split off as equally as possible. So with the mini splits, it does just basically T, but they've got a header there to control everything. But on the VRF, you just run a line set and Y everything off. So with the heat pump VRF, it's still just a suction line and a liquid line. There's nothing super complicated about it, other than you're going to use Ys to split off to the indoor units, and the whole system has to be in heat or cooling. What I'm going to focus on more when I'm talking about VRF right now is we're going to focus on the heat recovery. So instead of a heat pump system, which is all the units in cooling or all the units in heating, a heat recovery system can do simultaneous heating and cooling, if I can find my words. So a heat recovery system can do simultaneous heating and cooling at the same time. Now, to control that, you're going to need a few extra things than you're going to need in a standard HVAC system. So let me see if I probably should have pulled up this diagram first because I knew I was going to go that route. But anyway, you're going to have, instead of 2 lines, you're going to have 3 lines coming out of the outdoor unit. And all it is, it's actually really simple if you think about it, if you understand a heat pump system pretty well. All it really is I know they're showing, that's a heat pump. Where's the heat recovery diagram? All it really is you're running the discharge line out, the liquid line out, and the suction line out. So one of the lines is the discharge off the compressor. One of the lines is the suction line going back to the compressor, and one of the lines is the liquid line that is coming out of the condenser itself. So the only thing you have to remember there, though, is we don't call them those three because for one particular reason, and that is the. I'm just trying hard to find a diagram here. The do I got tiles? I got tiles. All right. We don't call them that because in cooling, if you're running the whole system in cooling, the discharge line doesn't need to be able to provide heat. And since that's the case, they use the line that is the discharge line and switch that over to a suction line. So going back to what I said, you have three lines, right? The three lines are really, these are what I want you to remember to call them, and this is something I'll definitely ask a question on. So the three lines are the high pressure, low pressure line, which is that discharge line that is sometimes your second suction line when you need a lot of cooling. So it's a high pressure, low pressure gas line, right? High pressure, low pressure vapor, whatever you want to call it. High pressure, low pressure gas, high pressure, low pressure vapor, or just high pressure, low pressure. But it's high pressure when something can call for heat, and it's low pressure suction if everything's calling for cooling. I can't believe none of these have a diagram in it. The second line is your low pressure gas line, which is your suction, right? And the third line is your high pressure liquid line. So those are your three lines in a heat recovery VRF system. Now, the thing about VRF, especially heat recovery, other than that, is as you guys see me flipping through all these pages, there's a lot of installation instructions. This is the other thing that's common between mini splits and VRF, and that is the fact that you really need to understand the manufacturer's instructions when installing the equipment. It is critical that when you are installing this equipment, VRF and mini splits really, that you are familiar with the manufacturer's requirements are for the installation. Mini splits, for instance, there is a so there's your 3 pipes on that. 3 pipes, outdoor unit, has 3 pipes coming out of it. Smallest line is the liquid line. The biggest line is your suction line. The medium sized line is high pressure, low pressure line. It's critical you understand the manufacturer instructions because mini splits, for instance, the distance you have to be from walls, and especially the distance you have to be from a ceiling. I remember for a while there, I would do a lot of Daikin mini splits because they had a very small clearance that the manufacturer required to the ceiling as opposed to some other units. And you need to know what their required clearances are. You need to know if you're going to duct a mini split, the small ducted ones, you need to know what their static pressure capabilities are because they're relatively low. Same thing with ducted VRF systems. A lot of them have a really low static pressure that they can maintain coming out of the ductwork. You need to know what the minimum length for the line set is. There's mini splits where the minimum length is 6 feet. There's mini splits where the minimum length of the line set is 15 or 20 feet. And if you go under that, you risk compressor damage. So manufacturer's instructions are critical. So when we're looking at these, just understand that I'm going to talk a lot about Daikins here, but manufacturers can vary and their wiring is different. Mini splits are pretty universal in their wiring. VRF, every manufacturer has a different requirement on its wiring. And then how long your line sets can be, what size the line set has to be joint to joint. All these things have to follow manufacturer's instructions. Now, once you've done a few different manufacturers, you start to realize that they're still all pretty much the same. All right, cooling is cooling, and you have to be very careful about following their instructions to make sure you don't void any warranties. But you realize the overall mechanics of how the system work is really similar still from manufacturer to manufacturer. They're going to have their particular kits. They're going to have the different longest run lengths that they can have. They're going to have slightly different communication wiring going from unit to unit. But overall, the way the system works is really similar. You're generally going to have a variable speed compressor in at least one variable speed compressor in every outdoor unit. You're going to have another variable speed compressor or standard compressor. Usually a lot of the outdoor units have two compressors because we're usually talking bigger systems on VRF. You're going to have on heat recovery, you'll have branch selector boxes, which I have a picture up now showing that. This is a piping diagram that you would have to follow if installing this particular Daikin VRF. This is how it would look. And you'll have indoor units, and then you'll have the little Y kits that split the lines. So outdoor unit is pretty similar. The only difference on the outdoor units is when you had multiple Daikin, and I think a couple other manufacturers used to require an oil equalization line between outdoor units, but they no longer require that. They've gotten around that, and that is one big problem with when you're talking large systems or you're talking VRF in particular. Oil return is a huge problem. That's one of their biggest that's one of the biggest problems they have to overcome when they design these systems. Is you need to keep your suction pressure, you need to keep the velocity high enough that you're returning oil to the outdoor unit, you're returning oil to the compressor efficiently. And some of them actually go through special cycles where it just works to return oil to the outdoor unit, because when you've got all that line set and you've got a lot of lines running to different places and a lot of indoor units where the suction pressures are going to vary a little bit from unit to unit as it returns to the system, you're going to lose oil. The oil likes to travel through the system, right? So if it gets lost out here in a trap or something, the next thing you know, you don't have enough oil in your compressor and you're screwed. All right. So that's one thing they do have to overcome, but they've gotten pretty good at doing that. I've not heard of any VRF systems failing because of oil return issues. Doesn't mean it doesn't happen, but if you follow their guidelines on line set, I think they've got them sophisticated enough that they do a good job of returning oil. You will connect the outdoor units. The outdoor unit T kits sometimes look more like T's than the indoor unit Y branch kits, but they'll all connect together, and one outdoor unit will be the primary one. So if you got one outdoor unit, obviously that one's the master, but then if you have multiple, one outdoor unit controls everything, usually the biggest one, and then the smallest ones follow commands from that outdoor unit, right? Then you'll have the three line sets that go down, and I'll zoom in a little bit here. And you'll see on this particular diagram, right, half inch by inch and an eighth by 3/4 comes out of this unit. This would be a 10-ton unit. 3/8 by 7/8 by 3/4 comes out of this unit. That is an 8-ton unit. This is liquid line, half inch, right? Inch and an eighth line would be the suction or the low pressure gas line, and then 3/4 would be the high pressure low pressure gas line, or your discharge most of the time, or in needs of high cooling it will turn into a second suction line. So again, the three lines, you can always tell which one is which just by looking at the size basically, because one will be the smallest, that'll be your liquid, biggest will be suction, the other one will be high pressure, low pressure gas. Sometimes the high pressure, low pressure gas ends up the same size as the suction, but pretty rarely. Generally, they end up being different sizes. I say that as you look at the main on this one actually turns into 5/8 by inch and an eighth by inch and an eighth, and it did end up the same size from here down to here for 2 units. So this system in particular that they have drawn out here actually ends up the same size for the high pressure, low pressure, and the suction line until it catches 2 units, and then they split up to different sizes again. So if they're all the same size, that can make it if those two are the same size, it can make it difficult to differentiate which one is supposed to be which. But you should be able to follow that line to somewhere where they're different sizes and figure out which one is the high pressure, low pressure gas line. So you'll run those down. They run in a bank of 3. And then you'll Y off to branch selector boxes, right? And these branch selector boxes are what switch the indoor units between heating and cooling. So all that's really inside here is a bunch of solenoid valves. And those solenoid valves are either sending liquid to the indoor unit and suction comes back, or they're sending discharge to the unit and liquid comes back. So from your branch selector to your indoor unit, there are only 2 pipes. There are 3 pipes going into a branch selector, and there are 2 pipes coming out of a branch selector. And this is what allows you to switch between heating and cooling. Now you can have, they don't actually show one on here, but you can have 2 units connected to a single branch selector. So out of the branch selector, you could T off or Y off and hit another indoor unit, but anything after a branch selector has to be operating in the same mode at all times. So if you have 2 indoor units to 1 branch selector, both of those indoor units need to be in heating, or both of those indoor units need to be in cooling. Obviously, because you only have 2 lines going to each, and there's no way for you to make those do different things at the same time. But this branch selector, this unit could be in heating, and over here on this branch selector, this unit could be in cooling, and you wouldn't have any problems. If this one's in heating, discharge goes in that unit. It basically turns that unit into a condenser, and liquid comes back from it. And then in this one, if it's in cooling, liquid goes to that unit, suction comes back. That's an evaporator. Right, and you can switch them at will at that branch selector. Now, the other thing that I'll definitely ask you about is, what if you don't have a branch selector? On a heat recovery system, it is possible to run a unit without a branch selector. If you run a unit without a branch selector box, it can only be in one mode. It will only be able to work in one mode. And that mode is cooling, right? Because we always have a liquid line and we always have a suction line. The line that changes is the discharge line that can provide heat, may turn into a suction line. So if you ran it without a branch selector, and you tied it onto the discharge line in the liquid line, sometimes the unit would heat and sometimes it would cool. But you'd never know which it would be, because it all depends on what time of year it was. 90% of the time it would run in heating, and then at random it would run in cooling. So you can run a unit without a branch selector, but that unit is cooling only. Other than that, that's the basics of the piping. The important thing with the piping on this is that if you can see, and I know it's probably hard, if not impossible to see, but if you can see on this drawing, the other thing they have is distances. So it's 50 feet here, it's 10 feet here, it's 10 feet here, It's 10 feet here, so on and so forth. What they're showing on these piping diagrams is the distance from Y to Y, right? T to Y, Y to Y. So when you're installing these, especially if you're doing like install only and you haven't taken many classes on them, like you're working under a guy that's taken a class, it's pretty important to make sure that you know the distances to each split on these units, no matter what manufacturer you're working with. You have to know the distance of each section of line set until it gets to another component. So from the outdoor unit to the first Y, how many feet of line set is that? From that Y to the branch selector, how many feet of line set is that? From that branch selector to the indoor unit, how many feet of line set is that? And so on and so forth. And that is so that you can calculate the size of the line set, because how many tons is connected to it, which is one of the most important factors, dictates the size of your line set. So the more tons connected to that line set at a particular point, the bigger it's got to be, right? The longer the line set is, the bigger it's got to be. And if you get too far, you may have a problem. You may get primarily an oil return problem, right? Or too much pressure loss if it's not sized big enough. But if you size it too big, you'll get oil return problems. So the sizing of VRF systems is kind of like you got to get just that Goldilocks number on the size of the line set. If it's too big, you're going to have oil return issues. If it's too small, you'll lose too much pressure or capacity. So it's imperative that it's calculated what the size of each piece of that line set needs to be. Now, some manufacturers will give you the ability to use some software so that you can change the distances and see if it changes the size of the line set. Carrier used to do that. I don't know if they still do. I believe if you take Mitsubishi's class, they give you that ability. LG, I think, offered the software. I've never used LG's software though. Daikin, it has to go back to the designer. Generally in our area, back to Hvac. And they will check and double check every time you make it change to the length. They'll make sure that the line set stays the same. So it's kind of critical that if you're installing pipe for one of these systems, you account for every fitting, which Richard Van just brought up, and we'll talk about that in a second. But you account especially for the length of the line set, and that means to plan ahead. So, if you're installing this system and it's not 50 feet from the outdoor unit to the first unit, it's 80 feet, then you need to report that information back before you install the line set and make sure that's going to work. And if it's actually 20 feet from that Y to this Y, then you need to report that back before you bother piping it. So you need to have a good layout of what you're going to do before you do it, and report that information back to the engineer so they can make any necessary changes before you do it. So it's really important to kind of lay everything out, have a path, put up all your hangers and stuff first, and then after you've got a good plan, go and do it. A change of a few feet here and there usually won't make a difference, but it might. So you need to know. Now, Richard brought up he did an install where too many 90s, and there was too many 90s in there, and the pipe size ended up having to be upsized. Every 90 is equivalent feet, right? Every 90, I think, counts for 5 equivalent feet or something like that. So that needs to be taken into account too. Here's the rule with VRF piping. If you can avoid a 90, don't use a 90. Just use pipe. I don't care if it looks ugly. Okay, I don't care if it's not as pretty as you'd like it to be in the ceiling. Um, if you ever take a VRF class or talk to a VRF tech, somebody who works for a manufacturer or something, they love talking about when they have the plumbers do the line set. The line sets look real pretty, but the plumbers put in 4090s and nothing works right. It happens. Okay, it's when it comes to VRF and mini splits, but especially VRF, my rule is I don't want it to be pretty, I want it to be practical. It should be good workmanship, you should do a good job, you should make it look as good as you can, yes. But if it's going to be a little bit uglier, if I just kind of beeline it from the Y kit uh, to the indoor unit, or I can make it look real pretty by adding 390s, I'm just going to beeline it. It's better practice. You want to, I mean, it's just like anything else. Ideally, you keep the line set as short as possible, basically, right? Um, so it becomes much more critical when you're not keeping the line set as short as possible to one unit. You're keeping as short as possible to 50 units. So don't worry so much about adding a couple 90s to make it look good. If you need to put in a 90, try and bend the copper to make the 90. Don't use an actual braze 90. Um, the other thing that comes up a lot with these is minimum distance between components. So if you look at this diagram, it shows 2 feet from this. Oh crap! It shows 2 feet from this Y to this branch selector. That's pushing it. Alright, 2 feet is like your minimum between components because you need room for that refrigerant to um, lose its turbulence, basically achieve laminar flow again as it hits a component, because there's going to be turbulence in that piping. Try and think of refrigerant in a VRF system the way you think about duct. You know what I mean? Um, Duct it's real easy to picture the air if you go a 90 then a 90, or if you go a branch and then a 90 immediately, right? Then you're going to have turbulent flow in that 90 and you're going to get less airflow than if you used a nice high efficiency takeoff and then, ran smoothly after that branch. Refrigerant's the same. They're both liquids, okay? Fluids. Air is a fluid. Refrigerant is a fluid. Water is a fluid. They all behave very similarly. So anything that causes turbulence in one system causes turbulence in another. The only difference is the pressures we're dealing with and how much that turbulence really affects the ability to get that fluid from one place to another. And with VRF, we won't really lose the ability to get it there, but we can still cause turbulence that'll especially cause noise. Like if there's a lot of turbulent refrigerant flow up to one of these branch selectors when the solenoids are opening and everything, you'll hear it, the refrigerant hissing and stuff more going through the branch box. So you want to keep a minimum distance of generally 2 feet from component to component, but you also want to keep the lines, again, basically as short as possible outside of that to each component. So you want to give you that minimum distance, but not be excessive. There are instances in which it does help to kind of run the line a little bit farther and go around, but those are pretty rare. That's usually to just try and keep the line the same size. And if you've got 10 feet here, but if it's written down as 10 feet, but you could really do it in 5, then maybe try and run it just a little bit longer so you don't have to double check it. But rarely does this size change if you're going to a single unit. No matter what you do, it's usually going to be the same size from the branch selector to the units. It's these long runs that can be kind of weird. I can't remember what it was, but I remember one time we did have to try and keep the line set a little longer from one unit to another. I think it was just so we could keep the minimum distance, and it ended up making it, instead of like a 3-foot run, a 10-foot run. But that was because we needed 2 feet between two branches, if I recall, and it's just how it turned out. There's a bunch of other piping considerations to think about. One more actually, before we go too far, is on these Ys. Where's a picture of one of these Ys? On these Ys, they need to be level. And again, this goes back to thinking about refrigerant as a fluid. Okay? So when you install a branch kit, and they don't all look like this, but this is what the Daikin ones look like. This should be as level as possible. You can go straight up and straight down. You can go level sideways, but you can't go too far out of level or up and down like this when you split. The reason for that is, again, what we're trying to do is we're trying to split this refrigerant flow evenly, and there's going to be some liquid and some gas in the pipe pretty much all the time. We're never going to have a perfectly superheated vapor or perfectly subcooled liquid, especially on line sets this long when we're varying capacity. So if the liquid is flowing down and hits this portion where it splits, it should split relatively evenly between these two pipes. If these two lines are converging and it comes down, they should both enter this pipe kind of evenly. If the liquid is coming through and hits this evenly, it's going to split evenly. But if the refrigerant is running along the bottom one here, it's not going to want to tend to go up this pipe, and you'll get mostly gas in this pipe and mostly liquid in this pipe, and that is a bad thing. And pretty much all of them will tell you it can be installed vertical or horizontal plus or minus 30 degrees, so they say it can be off by 30 degrees one way or the other, but anytime you take the actual class, they'll tell you no, it pretty much has to be level. Don't play with having it 15 or 20 degrees off. Make it level. So that's one real good lesson from VRF as we talk about all this. Learn to think about refrigerant piping as if there's liquid and gas in it, and when you're running it, think about where the liquid would go and where the gas would go. And if you're trying to split a line or something, because they even have mini splits now where you can split the line set as if it's VRF, when you're doing systems like that where you're splitting line sets, you should think about, okay, what happens when I split the line set this way? Is it going to be an efficient way to split the line? Learn to think about the turbulence in the line. And, thinking about the refrigerant pipe as ductwork in this case. How is the turbulence in the line going to affect how the refrigerant's flowing through the pipe? Now, that's most of the quick and interesting things when it comes to the piping. Like I said, there are a bunch of rules here. There's length limits. There's distances. Like I said, pretty much like it's talking about here. Elbows and headers should be kept 20 inches from indoor units. You generally just say 2 feet. Elbows and headers should be kept 40 inches from branch units. But again, this is kind of different from manufacturer to manufacturer. But your rule of thumb is 2 feet component to component is the least you go. And then for Daikin to the branch boxes, they basically say 4 feet. But these are your absolute minimums. All the pipes need to be insulated. The liquid line, the biggest reason for the liquid line being insulated is so you don't have heat loss through that huge run that you're going to have, because you're talking about hundreds of feet of liquid line. You will have heat losses in it, and the other two should be obvious because both could be suction at any time, and the discharge line could be hotter than you'd really want it to be. So there's a bunch of other rules there, but those are kind of the neat ones that might give you some things to think about the next time you're looking at refrigerant pipe and how to run it and what your options are. Learn to think about things, especially when you're working on VRF. Try to learn to think about things a little bit more utilitarian, so that you're doing what's best for the system, not necessarily what's best for aesthetics. How it performs is more important in the end than how it looks. That doesn't mean poor workmanship, but that does mean thinking about it in a way that's going to maximize your possibility of having a good working system. And then learn to think about different fluids, how they would operate in a different environment. So again, being able to think about the turbulence in the refrigerant pipe, being able to think about, it's good to picture water flowing through the refrigerant pipe and where would the water go, or picture a liquid and gas mixture, where would the liquid go, where would the gas go, because if you get good at picturing those things, you will hopefully get good at spotting where you may have a problem in the system, because of how things are ran, or why the refrigerant might be noisy at a particular part. If you got 390s back to back and the refrigerant piping seems real noisy at that point, well, it's probably because you have 3 elbows back to back and there's a lot of turbulence in that section of piping. Wiring, talking wiring real quick. Wiring is different from manufacturer to manufacturer. So follow that manufacturer's specific instructions when it comes to wiring. I haven't, unless some of them has changed. Every VRF manufacturer is different, and anything I tell you about one won't be true for the other. And that's just the way it is. The Daikin is probably the simplest one because it's 2-wire unit to unit. 18 gauge stranded, not shielded wire goes from in basically a daisy chain throughout the system. But Carrier's different, Mitsubishi's different, LG is different. So when it comes to wiring, I don't want to dig too deep into it, because anything I tell you will probably not be the same if you're working on a different manufacturer. Now, one thing that is common between them is to try and avoid splices. And if you do need to splice wire in the system without landing it on a terminal, then you will want to ideally solder those wires together. If you have to make a splice in the system, twist them together, solder them up real good, and make sure you got a really strong connection. And the main reason for that is basically how these units tell which unit it's communicating with, because it's just sending a DC signal to every single unit. Is think of it as, and this is probably an oversimplification, but think of it as the outdoor unit, or wherever you're communicating from, is basically testing the resistance or testing the time it takes from when it sends a signal from one indoor unit and when that signal comes back. So from the branch selector and back, and from that branch selector to this unit and back, and from the branch selector to that unit and back. So if you have any connection that's going to vary in resistance, it's going to delay that signal, and if the resistance has even a little bit chance to get better at some point, it's going to make that signal quicker. So you're basically going to have miscommunication, because the outdoor unit's saying, okay, if I send this signal to unit number 1, it should be back in a second, and it sends it to unit 1 and it comes back in 2 seconds, and then it sends it to unit 1 again and it comes back in a half a second, because you got a wire nut that's not made well on the 2 wires connecting or something, and it gets confused. It gets a communication error. So you need to make sure, if you splice the wire, you do the best possible job of making a completely solid splice, and even if you do that, you may have some problems. So it's better not to splice at all, but if you absolutely have to, use the most solid connection you can. I have had luck with doing like a little terminal block and splicing together on a terminal block before, and I've had luck soldering them, and I've had bad luck wire nutting them or putting them on a terminal block. So your mileage will vary when you have to make a splice, so just try to avoid it in general. Any questions on any of that stuff so far? Alright, so let's talk about a few other things when it comes to installation of mini splits and VRFs, and hopefully this will be slightly more useful than some of the basic outlines I just went through. I know if you guys haven't installed them, what we just talked about may or may not come into play for a few years, but it's important to understand the system so when you roll up on it, you know how it works and it's not too complicated seeming. But when it comes to mini splits and VRF, there's some important installation lessons you'll learn if you install one of these systems. The first thing I wanted to talk about, but I can't find the slide on it, and I think I'm on the wrong document. It's not that, it's this. Alright, the first thing about it is VRF and mini splits do not use the same oil as your typical 410A system. So if we're talking residential or commercial unitary systems, as a lot of people like to call them these days, basically standard systems, you know, RTUs, split systems, things of that nature, most of our 410A systems use POE oil. Alright, mini splits in VRF tends to use PVE oil. There's some differences between POE and PVE, and honestly I think the PVE oil is the better of the two, although I'm not an engineer and I can't tell you which one is actually better from a manufacturer's perspective, but I believe it would still be the PVE oil, the one they use in the mini splits and stuff. POE, both of them are very hygroscopic, right? So both of them attract water a lot, right? We all know that when you open up a system with POE oil, you have to be very careful because that oil attracts water very fast, and when it attracts the water, it bonds with the oil, and that creates acid in the system over time, right? So we call that hydrolysis. All right. PVE oil is way more hygroscopic than POE. So as soon as you open it up, you're going to get a lot of moisture in that oil, and there's going to be nothing you can do about it at that point in time. It's just going to attract any moisture in the air very, very quickly. But the thing is, with PVE, you have minimal hydrolysis with it, right? It's very hygroscopic, but with minimal hydrolysis. So you're going to have less issues with that oil forming an acid quickly. It's still going to be a problem though, right? You're going to have moisture in the system, and that moisture is going to create problems being in the system. The thing is, with PVE oil, that moisture is relatively easy to remove. It's going to take longer to remove it during a vacuum than it normally would, because that moisture gets in the system and it stays in there. But it can be removed under a vacuum. With a POE oil, with the regular POE oil, basically once that moisture's in there, it's almost impossible to get out. All right, it's basically there, which is why you need to really try and work as quickly as possible when you have a POE system where the system's open. And if it's had a long amount of contamination in it, really you should be changing the POE oil. With the PVE, I've seen mini splits that had issues where the suction line was basically going into negative pressure, so it was sucking air in through a leak, and it had tons of moisture in the system, and it took like 36 hours of having the vacuum pump hooked up, but it eventually hit 500 microns. With POE oil, it can be exceedingly difficult sometimes to get you down to a decent micron range once that oil's in there. So what I want you to remember off of POE versus PVE, POE oil, it's extremely important that you just minimize its contact with moisture as much as possible. With PVE, you still want to do the same, but you won't have as many issues when that moisture gets in there, as long as you perform a good vacuum. Now, with that being said, we can talk about performing a good vacuum, right? Performing a good vacuum is important. We haven't really discussed that much so far, so let's talk about what you should do to perform a good vacuum. And everything else we're going to go through from here on out is going to be in relation to commissioning a VRF system, but they are good practices even with standard systems. So number one is, after you've got everything hooked up, well, first off, installing piping. When installing refrigerant piping, you should always purge with nitrogen. We'll get to vacuum in a minute. Let's talk about piping installation real quick. You should always purge with nitrogen. On small systems, you can get away with not purging and you'll have minimal problems. When you're talking VRF systems, you have so many joints, you are going to have a nightmare if you don't purge while you're brazing. So if you kind of like to cheat sometimes and not purge while you braze, never ever install that system without purging with nitrogen, and never ever let your buddy do it either. Okay? You're just going to create a bad time. Alright? So if you see a guy that's not properly purging while he's brazing, and it's a big system with a lot of joints, stop him and tell him to do it right. And that goes for any system, really. You know, if you got to do a joint or two, you know, I'll look the other way if you got to do a couple joints and you don't purge. It's not good practice, but I don't mind looking the other way. Alright, if you're going to do 10, 15, 20 or more joints and you're not going to purge while you're brazing, you're begging to have a problem. So don't do it. Alright? After you're done brazing, you want to do good leak detection. And good leak detection is putting the system under a pressure test for as long as possible. It is extremely important when you're dealing with a system with a lot of joints that you do the best possible job on checking for leaks. And a VRF system is a very good example of a system that's going to have a lot of joints. But again, if you're doing a commercial split that just has a long run with a lot of fittings, it's the same principle. Every joint's going to have some amount of leakage to it. Systems have some leakage no matter what you do. There's leakage through the copper pipe, alright? But there's also leakage mainly through every braze joint you have, every flare connection you have. Anywhere where there's a weak spot, you're going to have more leakage than you would otherwise. And the only way to minimize that leakage is to do a pressure test and to catch as many of the larger leak points as possible. Hopefully there are no large leak points, but there may be, so you need to find whatever you got. So you want to do it on every system. You want to do the longest pressure test that time will allow. And, you know, I know most systems you're not going to be able to do a 24-hour pressure test, but if you're able to do a 24-hour pressure test, then do it. All right? If you're not able to do a 24-hour pressure test, do the longest pressure test you can. And your pressure test should start at about 50 to 150 psi. Let those sit for a couple minutes. Make sure you have no leaks. Take that system up to 300-ish psi. Let that sit for a few more minutes. make sure you don't have any leaks. Then take the system up to whatever the test pressure is, and if the test pressure is less than 300 psi, maybe stage it a little bit, but most of our systems are 410A right now, so most of them have a test pressure of at least 450. So then take it up to the maximum pressure allowed for test pressure and let that sit for as long as possible. If as long as possible is 15 minutes and you've got a good sensitive gauge, then fine, it's 15 minutes. If the longest you can let it sit is 2 weeks, let it sit 2 weeks. The longer you can test, the less sensitive of a gauge you need to find your leak. If you can only test a system for a short period of time under nitrogen, then make sure that you have a good quality, accurate gauge so that you can see if there's any leaks. If you don't have good gauges, then make sure you let that pressure sit on there as long as possible so that if you have a leak, you'll detect it. And get you good at using soap bubbles or trace refrigerant or whatever your favorite method is, ultrasonic, whatever it is, get good at a method of hunting down those leaks. I am partial, after trying a bunch of different methods over the years, I'm still kind of partial to just soap bubbles and nitrogen, but whatever floats your boat, whatever helps you find a leak when you got it. So do a good pressure test. After that, no, not after that. Let's talk one more thing. When you're leaving pressure on a system for a long time, let's dispel a myth here. A lot of people say that nitrogen does not change pressure with temperature. That is a load of crap. LG had us triple vacuum the system and hold the vacuum under 500 microns for 24 hours. We'll talk about that in a minute. Jesus, that is crazy. Okay, but technically you should be able to do it. Anyway, a lot of people say nitrogen does not change pressure with temperature. That is a lie. Every single gas changes pressure with temperature, no matter what you do. Some things will be more or less affected by temperature changes, or more or less noticeable. Air, when you put air on a pressure test, it's more noticeable because you have a lot of different components in there. You have nitrogen, oxygen, water vapor, and all of these things react differently to the temperature change. But any gas changes pressure with temperature. It is the gas law, okay? What is it? Boyle's? I forget. Okay, I'm not that good with it off the top of my head. But if you know your gas laws, you know how to calculate the pressure difference from the temperature difference. Here is a little cheat sheet. Screenshot it or something if you want to. This is a pretty good cheat sheet on knowing the pressure difference that you're going to have after a temperature difference with nitrogen. Above 300 psi, you're going to have noticeable fluctuations. Under 300 psi, the pressure change is usually small enough that you probably won't notice it anyway. Unless you have a very accurate gauge, you're probably not going to notice the pressure changes with the temperature below 300. But once you get above 300, you've got such a large amount of pressure in there, the temperature changes are going to affect it more. So you can use this formula to compensate for temperature drop or rise from one day to the next when performing a 24-hour or longer pressure test. Make sure you always record the temperature of the piping components when you do this. So if most of your line set is in a temperature controlled building, like the building already has air conditioning in it, so most of the line set stays at 70 degrees the whole time, you probably won't notice much of a pressure change, right? But if the whole building is unconditioned and one day it's 70 degrees and the next day it's 40 degrees, you're going to have a pressure difference, right? And you need to know if that's a leak or if that is just a change because of temperature. So record the temperature when the system is pressurized, subtract the temperature when the pressure is checked, multiply that by 0.8 and you get the pressure drop. So this is a good little cheat sheet. So basically your pressure is going to change about 0.8 psi per degree of temperature change. Alright, So it's not much, but it's something. And if you're talking a 20, 30, 40 degree temperature difference, then that is a 15, 20, 30 degree pressure difference. So that's a good way to shortcut instead of doing the whole gas law equation. It can still be done if you know the gas law. It's not that difficult, but this is still way simpler. Now, after you have done that, we go to vacuum. When it comes to vacuum, it's important to be able to perform a good vacuum. Alright, and it's even more important when it comes to VRF, because again, you're talking about a big system. You need it to be tight, dry, factory quality. Alright, but every system, ever since I learned VRF installation about 10 years ago, I have been as anal as possible about good vacuuming practices, good evacuation, because it's really important. It's probably one of the most important things you do, is make sure there's no air or moisture in the system and there's no contaminants. So you make sure that you put the piping together without having any dirt or debris get into the system, and then you make sure that when you're done, you evacuate the system completely, have no moisture in there, you have no leaks. Having a good vacuum hold for a long time basically double ensures after your pressure test that you don't have any leaks, and you end up with a system that should hopefully never need to be opened up for service until a component fails for some other reason. And ideally that's not the compressor, because if it's charged right and installed right and everything else, then you shouldn't really have a compressor failure theoretically, right? So the better you install a system, the less likely you are to have problems with it. And when you've got a system with 40, 50 components, you really want to make sure that it's installed to the best of your ability. So once you get all the piping done and installed correctly, you want to evacuate it. It is important to make sure that you're on this system. They recommend on VRF. They recommend a 2 CFM minimum vacuum pump. The CFM of the vacuum pump is not as important as trying to make sure that you have good hose connections. Hopefully a good vacuum manifold, not a refrigerant charging manifold, unless it's a good refrigerant charging manifold that's made to also be used for evacuation purposes. Getting full flow, they're popular at this point, but the Schrader removal tools that you can take the Schraders out while you vacuum save a ton of time when you're evacuating. And if you've got like that 7 or 8 CFM vacuum pump, you might actually be able to use some of that capacity, whereas if you're only pulling through a Schrader valve, you're probably only pulling at about a half a CFM anyway. You need a good digital micron gauge that you trust the readings on, which reminds me, I've got to clean my gauge tonight because it's a little contaminated. It's still okay, but not great. Got to clean my gauge. Good digital micron gauge. Ensure your hoses are in good condition. Ensure your gaskets are good. And what they don't tell you here, but I will tell you guys, is Nylog. Nylog is your friend. So when you're vacuuming, put a little bit of Nylog where all your hoses and everything connects, or if you're using solid copper, where your copper lines connect to your system. Put a little Nylog on those flares and you will have a much better time of it. It helps way more than you would think. Alright, a little bit of Nylog. And then if this is instruction for a triple vac. If you're having trouble vacuuming down a system, like it's a bigger system, or it's been open for service, a triple evac does end up being faster a lot of the time. I'm serious. I know it seems like it's counterintuitive to break that vacuum with nitrogen and then start vacuuming again, but if you do it a few times, you will find that a triple evacuation will actually save you time in the long run if you're dealing with a system that's been open for service or has some moisture contamination from just being open for too long or something. Ideally, it's closed off all the time, but sometimes that doesn't happen. So evacuate the piping down to about 4,000 microns. Hold for a few minutes. Make sure it says 15, but hold for a few minutes under at about 4,000, and make sure you're not rising all the way back up to atmosphere. If you rise it back up to atmosphere, you probably have a leak. You need to leak check again. But if you hold around 4,000 and everything looks good, and then you probably don't have a leak. You still might have a really small one, but you probably don't. So then break the vacuum with dry nitrogen to a level of 2 to 3 psi and let the nitrogen flow through the circuit and then out the other side. So you kind of want to purge the system with nitrogen at low pressure. You don't want to open it before the system's pressurized because you don't want to draw air in, but you kind of want to purge the nitrogen in one line and out the other to try and just kind of carry some of that moisture out. Then evacuate the system again down to about 1,500-ish microns. Hold for a few minutes, make sure you're good, break it with nitrogen again, and purge it around. Then evacuate the system to 500 microns or less. If you can get down to 500 microns, you're pretty good on leaks. You may not be perfect, but you're pretty good. And you got a pretty dry system. The ideal is to, after you get it down below 500 microns, to hold somewhere below 500 microns for an hour. That doesn't mean go down to 220 microns and watch it slowly rise to 500 and it takes an hour to get 500. That means you should hold pretty damn steady at some point below 500. If you can hold that for an hour, that system's good. LG and Carrier both have extremely ridiculous desires when it comes to your vacuum. Holding down below 500 microns for 24 hours is fucking insane. I mean, I don't know, man. I've never tried it. I guess you could. I'd be so scared somebody would accidentally touch a hose and cause me to suck a bunch of moisture in the system for that long. I mean, all it takes is some temperature change, right? And your rubber gasket kind of changes a little bit. It expands or contracts, and then you've got a leak. Came back to a smoking vacuum pump. Yeah, I mean, it's crazy, dude. The first VRF system I did, we ran 2 vacuum pumps on it for a weekend. All right? 2 vacuum pumps on it for a weekend to get down to where we did. And we got that thing down tight and it held way below 500 microns. But it was tough, right? The last one I did, which was only a 4-unit system, actually went beautifully. I got that thing, took out a couple cores, got that thing down to, 220 in a few hours and held, for an hour easy. But anyway, sometimes they're harder, sometimes they're easier. It depends on how long it's been open and so on and so forth. But it doesn't take much to make a vacuum leak. So holding below 24 hours is ridiculous. But if you can hold below 500 for an hour, you're pretty good. You have very few leaks. Again, you're always going to have some leaks, but you'll have very few leaks. You should be in good shape. The system is tight and dry, and you're good to go. If you do that, get the habit of doing that on every system you service or install, you should have very few issues when it comes to system operation. You'd be surprised what just a tight, dry system can do for the quality of the install. They say, and honestly I believe it, they say 90% of issues with a refrigeration system is the installation. So that compressor dying after 3 or 4 years probably had a reason. All right. Doesn't mean it doesn't happen. I've had factory equipment kill a compressor in a year when everything was good on startup. So I mean, bad things are going to happen, but Bad things will happen a lot less if you do a good job on the installation of a system. So, nitrogen pressure test, good vacuum. Be very careful with POE, PVE. You can be a little bit more reckless on, but you still want to be careful to reduce the amount of time you have to vacuum. Do a good job, and you should be okay. Measure your line set. When it comes to charging, you have to charge mini splits and Vrf systems by weight. I recommend charging every system by weight. Charging by weight is my favorite thing in the world. I charge everything by weight. I don't use subcooling or superheat to charge a system initially ever. I may make an adjustment even after I weigh in a charge if the TXV isn't quite meeting its factory set superheat values or something like that, but that is few and far between. I charge by weight every time and almost never have to adjust it. And if I suspect problems in the system, I will pull most of the charge out, not enough to have to pull a vacuum on the system, but I'll pull most of the charge out till I get down below 10-20 psi. By the time you get there, you've got almost all the refrigerant out anyway. Get it down to about 10-20 psi, then weigh it all back in, and I know I got the right charge in it. I charge by weight. You guys do what you want, but unless you've got a system that's holding 50-60 pounds of refrigerant or something or I would say over 30. If you got a system that holds over 30 pounds and you don't have a recovery cylinder big enough for what you're doing, then I would not bother charging something in by weight. But anytime I'm working on a system and I'm unsure if the charge is correct, I'll just hook up a fresh recovery cylinder, take out most of the refrigerant, weigh it back in. You get good at it, takes less time than you think, and your charge is supposed to be right then. So if something is still acting funny, it's not the charge. Done. Easy. But you do have to know the length of the line set and make sure you add enough charge for your length of line set. And as a matter of fact, there should be a slide on that. Let me see if I can find that before we wrap up. Let me see if I can find the slide, because this is another thing that basically stays the same on every system you're going to work on. Alright, these numbers, you have to add the same amount of refrigerant for line set basically no matter what system you're doing. Okay, it really doesn't make a difference. And somewhere, and honestly it's something I always got to look up, I always forget, 0.6 ounces per 3/8 liquid line, I think. I always double check manufacturer's numbers. I can't remember anything off the top of my head anymore. I really can't. I gotta look up everything. But I always double check, right? You always double check. Alright, here you go. Refrigerant amount for field piping, 3/8 line set, 0.04. Maybe it does change a little bit more than I thought. I swear 0.06 most manufacturers, or maybe they changed this, I don't know. Anyway, it's generally pretty close though, no matter what you're doing. Field piping for any liquid line, 0.01 ounces per foot for a 1/4 inch, 0.04 ounces per foot, or pounds per foot, sorry, maybe that's what it is, 0.6 ounces or 0.04 pounds, whatever it turns out to. But this is get you close, you know what I mean? 0.015 pounds per foot 1/4, 0.04 pounds per foot 3/8, 0.08 pounds per foot 1/2 inch, 0.121 pounds per foot 5/8, 0.175 pounds per foot 3/4, 0.249 pounds per foot on 7/8. And that's probably close for just about every other system you work on, because no matter what system you're working on, besides what they added in for, which is usually 15 or 20 feet of line set from the factory, you need to add charge because of the line set, right? So you add that charge because of the line set. And when it comes to residential or split systems in particular, also make sure that the size of your evaporator doesn't change how much refrigerant you're supposed to have. I know looking those up so you can charge by weight can be a hassle when you've got all those factors to consider when you're weighing your charge in, but I'm telling you, if you know how many pounds are supposed to be in there, you're good to go, man. And when it comes to systems with microchannel coils or VRF systems or mini splits, you need to do it anyway. So it's better to be in a habit of doing something that can be done every time than something that can only be used some of the time. Now, I should have another video up on the YouTube channel that is practical considerations from VRF that has some of this information as well. So I'll post this video, but there'll also be that one if you want to look at that at some point and maybe glean a few more facts that maybe that I didn't go over as eloquently in this one. But that is some things that you'll learn if you've never done VRF. Those are some of the things that you will learn by doing VRF.